Today, we're going to talk about an element that went from being just a pretty color in a teacup to literally holding the power to shape our world. We're talking about uranium, and trust me, its story is packed with accidental discoveries, unbelievable power, and a future that is very much still being written. For over 100 years, this was pretty much the entire story for uranium. Before anyone even dreamed of atoms or fission, glassmakers figured out that if you tossed in a little bit of uranium oxide, you could make glass glow with this stunning, almost otherworldly green or yellow. They called it Vaseline glass, and it was a huge deal in the Victorian era. You'd find it in everything from fancy plates to jewelry. It was just this beautiful novelty, something that glowed under a black light, with absolutely no clue about the incredible power that was locked away inside. But here's the secret that was hiding in plain sight the whole time. That exact same element, the one they used for teacups, holds an almost unbelievable amount of energy. I mean, get this. A single kilogram of uranium fuel, about the size of a small pineapple, can generate the same amount of electricity as 1,500 metric tons of coal. That's a pile of coal as big as a house. This mind-blowing energy density is what turned a simple pigment into one of the most important and controversial resources on the entire planet. So what exactly is this stuff? Well, at its core, uranium is a naturally occurring silvery gray metal. It's actually the heaviest element that was forged way back in the birth of our solar system, and it is incredibly dense. We're talking 70% denser than lead. You can find tiny bits of it pretty much everywhere, in rocks, in soil, even in seawater. But its real power, its secret, isn't in its weight. No, it's hidden deep, deep inside its unstable atomic heart. So how in the world did we figure out how to unlock that power? Well, it wasn't a single aha moment. It was a scientific journey that unfolded piece by piece over about 150 years. The story really kicks off way back in 1789, when uranium was first identified and got its name from the recently discovered planet Uranus. For a whole century, it was just a chemical curiosity. But then there's this fantastic accident in 1896. A guy named Henri Becquerel leaves some uranium salts in a drawer, and he finds they've somehow fogged a photographic plate right through the paper. This invisible energy was later given the name radioactivity by the one and only Marie Curie. Each discovery just built on the last one. Ernest Rutherford came up with the idea of a dense nucleus at the center of an atom, and that set the stage for the final world-changing breakthrough in 1938. That's when Otto Hahn and Lise Meitner figured out how to do the impossible. They split the uranium atom. This process, fission, unleashed a truly staggering amount of energy. The atomic age had officially begun.
Okay, so we've split the atom, but using that energy on an industrial scale, that is not simple. You can't just dig uranium ore out of the ground and toss it into a reactor. It has to go through this really complex, multi-stage process we call the nuclear fuel cycle.
To really get this, you have to know that natural uranium basically comes in two main flavors. Think of it like trying to start a campfire. Over 99% of what you dig up is like damp wood. That's uranium-238. It just won't burn on its own. But a tiny, tiny fraction, just 0.7%, is like perfectly dry kindling. That's uranium-235. It's fissile, which is a fancy way of saying it can be split and can sustain a nuclear chain reaction. So the entire challenge of making nuclear fuel is basically just collecting enough of that super rare kindling to get the fire going. So how do they do it? Well, it all starts with mining the ore, which then gets crushed into this bright yellow powder, weirdly called yellowcake. Now, to separate the two types of uranium, you have to turn this powder into a gas. Then comes the really wild part. That gas is spun at insane speeds inside thousands of centrifuges. Just picture a salad spinner for atoms. This slightly heavier U-238 gets flung to the outside wall, while the lighter, much more valuable U-235 stays closer to the middle. You have to do this over and over and over, but eventually you increase the concentration of that U-235 from less than 1% up to the 3 to 5% that's needed for a reactor. And finally, this enriched uranium is turned back into a solid black powder, pressed into these small ceramic pellets, and loaded into long fuel rods, all ready to make some power.
All right, so after all of that incredibly complex work, we finally have our fuel. So how do we actually get electricity out of it? This is where we take that chain reaction and harness it in a totally controlled and sustained way.
Think of it like a perfectly controlled cascade of atomic dominoes. Inside the reactor, a single neutron is shot at a U-235 atom, causing it to split apart. This split releases a huge burst of heat, and this is the crucial part, 2 or 3 more neutrons. Those new neutrons fly off and split more atoms, which release more heat and more neutrons, and on and on and on it goes. In a power plant, this chain reaction is managed with incredible precision to produce a steady, massive stream of heat. And you know what that heat does? A very simple job. It boils water, which creates steam, which spins a turbine to generate electricity. It's the same basic idea as a coal plant, but with 1,000,000 times more energy and zero carbon emissions. Now, making electricity is uranium's main gig today. It accounts for about 10% of all the world's power, but it actually has a surprisingly diverse resume. That leftover U-238, the stuff we call damp wood, is called depleted uranium, and it's so dense it's used for military armor plating and projectiles. It's also what gives nuclear submarines and aircraft carriers decades of power without ever needing to refuel. In the medical world, research reactors use it to create vital isotopes for things like cancer diagnostics. And for scientists, its long, super predictable decay rate is like a geological clock, letting them date rocks that are billions of years old. So all of that brings us to today and to the future. You see, after decades where it kind of fell out of favor in many parts of the world, nuclear power is suddenly seeing this major comeback. So the big question is, are we on the verge of a brand new nuclear age? So why the sudden change of heart? Well, it's really being driven by three huge things. First off, energy security. Countries are waking up to the risks of relying on fossil fuels from unstable parts of the world. Second, climate goals. Nuclear power offers a ton of carbon-free electricity that runs 24/7, which makes it a perfect partner for renewables like wind and solar. And third, and this is a really big new one, artificial intelligence. The giant data centers that power AI are incredibly power-hungry, and they need a constant, reliable flood of electricity. That's a demand that nuclear power is almost perfectly suited to meet. And if you look at the projections, you can see just how big this shift could be. Right now, the world has about 440 gigawatts of nuclear capacity. And to put that in perspective, just 1 gigawatt can power around 750,000 homes. Now, based on the policies countries already have in place, that's set to grow pretty significantly by 2050. But if we're actually serious about hitting our net zero climate targets, that number would need to more than double. We're talking about a massive, massive expansion of the world's entire nuclear fleet.
And hey, this isn't just some theory or a bunch of charts on a screen. This nuclear renaissance is really happening. Huge new plants like Hinkley Point C in the UK are under construction right now. Dozens of other reactors are being built in China, India, and all across the Middle East. All told, something like 40 countries are now actively making plans to either build new plants or expand their use of nuclear power.
Now, a really key part of this future is a totally new kind of technology, small modular reactors, or SMRs. See, unlike the traditional giant nuclear plants that take a decade or more to build on site, SMRs are designed to be much smaller and, crucially, to be manufactured in a factory, kind of like an airplane. This could make them way cheaper and faster to get up and running, and flexible enough to power a single factory, a remote town, or one of those massive AI data centers. It's a fundamental shift in how we even think about deploying nuclear energy.